This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning. Usually before the midterm, there's a handful of students, so I always make a joke, we can go for coffee and just do a lecture in a cafe. Thanks for coming. So today I want to complete our discussion about complex sort of domain and how to use sort of complex plane or pole placement in this case to design controllers. From next week we will start talking about frequency domain. So we will start talking about Nyquist diagrams, body diagrams, and how to use these objects for analysis and design. So let's see. This is the outline of the lecture. I'll first motivate the material a bit. Then I'll talk about different ways in which we can decide where to place the poles. So how to choose desired pole locations for the closed loop. And then I will present the problem definition and solution for arbitrary pole placement. You will see that under very general conditions, we can find a controller that places closed-loop poles wherever we want, which is really a good result, really useful result. And then I will present an example that shows that pole placement may not address well at all the steady-state errors. So by combining pole placement with internal model principle, we can get a better sort of controller that addresses both the transients through pole locations and steady-state errors through internal model principle. And then we will just wrap up with conclusions. So we already talked about how to translate the specifications on step response into some pole locations in the complex plane for the closed loop, right? So what we also saw when we did root locus, that if we play with a single parameter, like in root locus, we cannot place poles wherever we want, right? So the poles of the closed loop would be right on the root locus, and root locus is a small subset of the complex plane, right? So the only locations where you can place poles using a single parameter is right on the root locus. So in today's lecture, we want to basically say, well, we want to place poles anywhere in the complex plane, right? Where obviously, whenever we have complex poles, we will insist that we have also complex conjugate, because in the end, the plans that we will be dealing with will lead to transfer functions that are rational with real coefficients. And in that case, poles would always appear with complex conjugate pairs. So we will see basically, so root locus has a single parameter, it's a static controller, right? It's like a proportional controller. And its ability to move poles is very limited. Now, if we allow dynamic controllers with more parameters, not just one parameter, but multiple parameters, then you will see that we can place poles arbitrarily anywhere in the complex plane by choosing the coefficients in the controller, right? So obviously the controller needs to be complex enough, of sufficiently high order, to achieve this. So before we talk about how to place poles, I also want to spend a bit of time talking about how to choose desired pole locations, right? So we saw one way of doing it is via dominant poles, right? So we translate overshoot, rise time, and settling time requirements into locations of closed loop poles, and we place dominant poles in that region, and we try to place all other poles far away from dominant poles. So that's one way of doing it, but there are other ways, and I want to talk about those now. So there are other ways of doing it. So suppose we are given specifications, and we want to translate these into desired pole locations. So the question is, what should be the set of closed loop poles if we are given a certain set of locations? Obviously, this is equivalent to choosing the desired characteristic polynomial, right? So if I just multiply all these, S minus Si, where Si are poles, I multiply them out, and I will get my desired characteristic polynomial. Now, note that this set of desired poles would always be admissible in a sense that any complex poles would always appear with complex conjugate pair. So the idea is, all right, we have a set of specifications. How do we translate that into a set of desired poles, or in other words, this characteristic polynomial? By the way, the locations of these desired locations of closed loop poles would completely determine the desired polynomial, right? So know that we never talk about zeros. We never talk about zeros of the closed loop transfer function. Although zeros will affect the performance, we saw that if there is an unstable zero, we might have undershoots. We will have undershoots, right? So we do not talk about how to play with zeros. In this lecture, we just talk about poles. I want you to actually get this early on. Although I will present several different methods, there is no reliable method, no single reliable method for doing this. Actually, choosing desired pole locations is still $1 million question, right? So we don't have a simple answer, unfortunately. In advanced control, we reformulate the problem in a different way. We don't say, let's find desired pole locations. We say, let's optimize a certain cost. So we have a cost that we associate to the system, and then we can find the best controller that minimizes that cost, right? So no other controller would give you a smaller value of that cost. This has to do with optimal control. It's a sort of it's departing from this approach of first specifying the pole locations and then enforcing those. It sort of is an indirect way of doing the design. If you do advanced control, we will talk about that. In one of the previous lectures, we saw we can do this thing, translate specifications into pole locations by thinking about second order dominant poles, right? And we want to now go through several others. So all of these are rules of thumb. None of these methods would be enough in general, but they are very good. They give you good guidelines. So that's why I say they are rules of thumb. So here they are. So we already talked about dominant second order poles, and today I will talk about Butterworth filter and prototype filter poles. And optimal control is something that I do in advanced control. It's an indirect way of doing pole placement, right? So all pole placement methods would need to be tested in simulation. So what you do is you first select desired pole locations by translating your specifications into pole locations. Then you design controller, and then you have to simulate to see whether you indeed satisfied the requirements that you set out to achieve. So you always have to test your design. It's never, straightforward. I mean, rarely it is straightforward. You might have to iterate on the procedure sometimes. Right? So I want to now talk about how to use these Butterworth and prototype filter pole locations. So Butterworth filter is a particular way of choosing the pole location. So these filters have certain properties, they give you a really flat sort of gain in the pass band, right? So when we start talking about body diagrams, this would become clearer. So there are certain criteria that are used to selecting poles of these filters. Now, Butterworth filters for, let's say, natural frequency equal to 1, let's say for first order system, the pole would be here. For second order system, the poles will be here. For third order systems, the poles will be here. Fourth order system, so N denotes the order of the system or the number of poles, and these crosses denote the locations of poles. Note that for every, let's say different order of the system, the poles are always located on a circle with natural frequency 1. Like I did choose here natural frequency 1. If you chose a different natural frequency, you would need to just scale. So the radius of this semicircle would be equal to omega n rather than 1. So this is sort of just normalized frequency equal 1. And you can actually keep going. I mean, you can find always, you give me the natural frequency, I can tell you, and give me the order of the system, I can tell you where these locations should be. Know that all these poles are always in the left half plane, right? We want to find stable system. And they somehow, sort of, how they are obtained, well, you divide this sort of half plane, right, into sort of angles that are sort of let's say, a specific value. So for n equal to, this angle here is pi 4. For order 3, angle is pi 3, etc. So if you know n and if you know your natural frequency, you can quickly plot the locations of these poles. You can also look at the polynomial itself. So if you look at the coefficients in the polynomial that corresponds to different Butterworth filters, then the coefficients in the polynomial for second order system is given here, third order system, fourth order system. So you just read out these coefficients, plug them into the polynomial that's given here, and you got your desired sort of locations of poles. So these things you can find in books, right, textbooks, and you can just read them out. What are the step responses for different Butterworth filters? Well, they are presented here. So the first order response is the blue one, and then second order, third order, fourth order, fifth, sixth. So you can see that the higher the order, you will have more and more overshoot, but they all settle, at the, steady state equal to 1. So the higher the order, they would oscillate more, and there will be more overshoot. The first order filter doesn't have any overshoot. It's just an aperiodic response. You have just one real pole. So if you, for instance, look at these step responses and you say, all right, I would be very happy if I design my closed loop system so that step response is like in this case. You can choose, sixth order Butterworth filter pole locations and enforce in your pole placement design exactly those poles for the closed loop. So that's one way to think about it, right? All right, there is another way of choosing desired poles, and this is a bit indirect. This is more similar to advanced control techniques. So what is this thing here? Well, think of this as a cost function. So you are saying, if I look at the difference between the reference value and the output, and I look at this particular integral, for different controllers, I would get different values of y for the closed loop. So each different controller would give me different value for E, and then if I integrate this, I will get a constant. This thing here is called the cost, right? So each controller would incur a cost. So the best controller in the sense of minimizing this cost is the one that gives you the minimum value for this, right? So there is no other controller that's better than that controller in that sense. So then this sort of prototype filter approach is exactly choose pole locations, right, for the closed loops that give you the best value of this cost, okay? So it's an indirect manner, and that's very, very similar to what we do in advanced control. We just use different type of cost functions here to design different type of controllers. I do that a lot, like maybe for 6, 7 lectures in advanced control. All right. In this case, for this particular value of the cost function, you can come up with characteristic polynomials for systems of different order. So how should you read this table? You tell me the natural frequency you want to achieve, right? Then you simply plug that natural frequency into these polynomials. If you want to have a closed loop system of second order, that's the polynomial. You need to choose the natural frequency. For third order, it's this polynomial, etc. So again, you have polynomials that are given to you, and you just need to sort of select natural frequencies. We talked about the importance of natural frequency for rise time, right? So you can sort of say, all right, if I want certain rise time, I want certain order of the system, then I can select the polynomial just from this table and specify what omega n is. If you look at the step responses of these sort of systems, you will get something like this. So note the difference from Butterworth filters. There's less overshoot even for high order systems, right? And maybe they are a bit sluggish. So for high order systems, you would get sort of this longer settling time, right? So it takes longer time to settle and converge to the desired reference. But again, depending on your application, you would look at this figure and say, okay, well, this sort of response looks good to me, and it's acceptable in my case, and then you pick that polynomial, and then you try to design a controller that enforces these closed loop poles, right? So again, this is just another rule of thumb method. All right, so what we've done, we discussed several different methods for picking the closed loop desired locations, right, of poles. And now we want to talk about how to design a controller that places closed loop poles in those locations, right? So we now want to talk about how to achieve these closed loop pole locations through design. And that's called arbitrary pole placement. By the way, in advanced control, I also do arbitrary pole placement using a slightly different method. So using static state feedback controllers, it's a different class of controllers. Here we would use dynamic output feedback controllers. So I measure output, I pass the output through a comparator, feed that error into the controller, and the controller will be dynamic, right? So the controller would have a certain transfer function. Know the difference with the root locus. In root locus, transfer function was trivial. It was just constant k. Here, transfer function controller would be dynamic, would be higher order in general. So we are considering the problem where we have a planned transfer function and we want to design controller transfer function. So B and A are given to you. They are obtained through linearization of some model around an equilibrium, right, by Laplace transform. And then we have a controller transfer function, and we want to design P and L. Moreover, what we assume in all of this is that I know what is the desired closed loop polynomial. I would assume that I know what I want to achieve. And that can be either dominant pole locations or Butterworth filter or prototype filter, or any other method that you come up with, right? So I would like to sort of first, so how do I get this characteristic polynomial? I consider this controller and plant to be in feedback loop with unit feedback, and I write what the denominator in the closed loop transfer function is. The denominator is exactly this, right? That's the closed loop transfer function denominator. Now, what I will assume is I will assume that I know this. I know A and B because my plant is known, and I want to design L and P polynomials in S so that this equation holds. So this is known, and that basically captures my specifications, what I want to achieve through the design. A and B come from the plant model, and L and P are basically defining completely the controller. So the design consists of finding P and L so that this equation holds. So, as I said, we assume that your time domain specifications were translated into specific desired closed-loop polynomial, and we want to just design L and P, knowing ACL, A, and B. Right. So what we can do is we can just write these polynomials as sort of expand them. Why I'm doing that? Well, I actually need to find this polynomial L and P, and what I mean by finding that polynomial, I need to find all of the coefficients in these polynomials to know what they are, right? So the unknowns that we are looking for are coefficients in polynomials P and L. So I know coefficients in polynomials A and B, and I know coefficients in polynomial ACL. That's the problem setup. So I know C i's, I know A i's, and I know B i's, and I don't know L i's and P i's. I need to find them. Right. So what we do now is we go back to this right-hand side. We multiply polynomials A and L and B and P. We cross-multiply them. We rearrange coefficients in the polynomial so that we can compare coefficients of this guy. Coefficients of this guy should be equal to coefficients of that guy. And the parameters we need to use is parameters in polynomials L and P. Right? So we just compare the like coefficients. So, by the way, we didn't yet specify the orders of polynomials NLP, right? So the controller may have so many poles and so many zeros. The question is, how do we choose this? Well, it has to do, the choice will have to do with the number of equations we need to solve, right? And how many parameters we have at our disposal to play with. So we will have some number of equations, and we will have some number of parameters. Obviously, if the number of equations is equal to the number of parameters, and some conditions hold, we will have a unique solution, right? So we will pick the order of the controller so that, it's smaller than order of the plant by 1. So if the plant order is n, we will pick the order of the controller to be n minus 1. If we do that, and then we compare, how many equations we have and how many unknowns we have, then we will see that we can always solve it, right, under very weak assumptions. I will state these assumptions in a moment. But at least, so for instance, just to give you an idea, if the closed loop characteristic polynomial is, let's say, 5th order, right, and I assume that the controller is just static, right, so then these guys are just like constant. So suppose that P is K and L is just 1, right? Then, obviously, I can't arbitrarily place the poles. The location of poles will be on the root locus corresponding to that case. So, but if I have more parameters to play with, then I can actually solve this equation, no matter what ACL is, no matter how high order this polynomial is. So what we will do in this lecture, we will always assume that the order of the controller is 1 less than the order of the plant. And we will see that under this condition, we will be able to solve the problem under very weak assumptions. So how do we do this? Well, we first, so if we assume this, we cross-multiply these guys and then rearrange this polynomial so that we can compare coefficients in this polynomial in S with these coefficients in this polynomial in S. We equate these coefficients. We can rewrite everything in this form. So what I have here is a matrix. Do you remember matrices? Right? So it's n by n. Well, it's actually the dimension of this matrix is higher than n. sorry. So this matrix S here has a specific form, and this is called Sylvester resultant matrix. So what you do is you arrange coefficients of polynomial A starting from the highest to the lowest, and then fill in zeros the rest. Then you put the 0 on top in the next column, and then start from AN, and again fill it in the same way, and then fill zeros when you run out of coefficients. And keep going until you get up to A0 to the bottom, and then you stop, and then you start filling B columns, right? And again, the same principle applies. So this matrix here, if this matrix is invertible, so its determinant is non-zero, then the inverse exists, and then we can basically multiply by S inverse both sides. Then this would be then identity. S inverse times S is identity. And then this would be S inverse times this. Now note that this thing here is known. These are the coefficients of the desired closed loop polynomial. These are the coefficients of the controller that we are looking for, right? And hence, I can solve this set of linear equations if Sylvester resultant matrix is invertible. Now, it turns out that the matrix S is invertible if and only if the polynomials A and B are coprime. Do you remember what's a coprime set of polynomials? Sorry? Can't hear you, sorry. Yeah, they don't have common roots, so there is no pole zero cancellation in the plant. Later on, in advanced control, if you do this subject, I will connect pole zero cancellation to the fundamental properties of controllability and observability. You will see in that subject that if there is pole zero cancellation, then either the system is not controllable or not observable, or both. These are fundamental properties, right? Controllability and observability, and they are fundamental for pole placement in particular. So anyway, to summarize what I've just said, if polynomials A and B are coprime, in other words, there's no pole zero cancellation in the plant, then we can rewrite, this set of linear equations this way, where S is the Sylvester matrix, and if these guys are polynomial, Sylvester matrix is invertible. And this implies that there exists unique solution of this is equal S inverse times that, right? So S is known because A and B are known. This vector here is known because the closed loop characteristic polynomial, desired polynomial, is known. And what we want to find, we can find, right? Because of the invertibility. So that's basically how the conditions, that would allow you to solve this problem are. I mean, comprimeness of these A and B is necessary and sufficient for, inverting this Sylvester matrix, and we can then solve the problem, right? All right, so let's just look at an example. So plant model is given here, right? So A is the bottom polynomial, and B is just 1. So we are saying now, since plant order is 2, we will pick a controller transfer function that is 1 less than the plant order transfer function. So the order of the controller would be 1. But I do allow both zeros and poles in the controller. And know that P1, P0, L1, and L0 are all 3 parameters that we need to design, right? So I'm then saying, let's suppose that we want to place the closed loop poles at -c, where c is positive, just for the sake of argument, right? Just for the sake of argument. And then if I multiply S plus C 3 times, I get this polynomial. So that's my desired polynomial. That's what I want to achieve once I close the loop with that controller and that plant. If I write the coefficients of the controller in the vector form like this, I'm looking at the inverse of the Sylvester matrix. So this Sylvester matrix, note what I'm doing here. The coefficients in the polynomial A are 1, 5, and 9. 1, 5, and 9, right? So then I put 0, and then I again do 1, 5, and 9, and then I stop because it's a second order system, right? So I just need 2 columns. And here I have 0, 0, 1. They are coefficients for B. Why? Because because the Planck order is 2, I actually think of this B as 0 times s squared plus 0 times s plus 1. Right? I still consider this as a second order polynomial in S. So that's why I have here 0, 0, 1. Right? And then the second column would be insert 0 first, and then 0, 0, 1 are the coefficients in the B polynomial. That's the Sylvester matrix. Note what's interesting about this Sylvester matrix here. It is lower diagonal. What is the determinant is just 1. Determinant is 1. So this matrix is definitely invertible. So we know that we can solve this problem because we can find the inverse of this matrix. If you do that, so this is the inverse. This matrix here, it turns out to be the inverse of the Sylvester matrix. You multiply this matrix with this vector, you get this. These are solutions, basically. If you let L1 in the controller to be 1, L0 to be 3c minus 5, etc., you get basically what the coefficients in the controller should be as a function of your constant c, right? C is the, minus c is the closed loop pole, right? So there are 3 poles at minus c. So basically we calculated P1, P0, L1, and L0 because L1 is this, L0 is this, P1 is this, and P0 is this, right? So that's the solution to the problem. In the end, you get a set of linear equations, and you just want to be able to find a solution, right, to this set of linear equations. I'm just doing it using matrix calculus. All right. So note that controller, this is perhaps not so important, but controller itself is unstable. I did have students ask me, oh, but if Planck is stable, I don't have to worry about stability. You often need to use closed loop for robustness purposes or for some other purposes. But then if Planck is stable and controller is stable, you may have that the closed loop is unstable. Actually, any set of possibilities is possible. So you may have unstable controller and Planck, but the closed loop is stable. So this is just sort of a remark that controller is unstable for C smaller than 5/3. Now, note also that when we look at the open loop, so what is this lambda 0? This is basically product of the Planck and control transfer functions. That's like the open loop transfer function, right? Evaluated at 0 is equal to this. In other words, complementary sensitivity transfer function evaluated at 0 is equal to this. Know that this is actually the formula for the closed loop transfer function, right, where lambda 0 is the open loop sort of transfer function, right? So note that because of this, you may have that for different values of C, you may have very bad steady state error, right? If you think about now applying final value theorem, then this might indeed lead to very poor steady state errors. Why? Because in the steady state errors, we want to assure 0 steady state errors for step preferences. We will need to have complementary sensitivity equal to 1 at 0, right? Complementary sensitivity at 0 should be equal to 1. And if you simulate for different values of C, so what is given here is step responses for C equal 1, C equal 3.8, C equal 10, C equal 4, you can see that the final value, steady state value, look here, it's 0.0156, but we want this steady state value to be at 1, right? So the error is huge. Here, you have that steady state value is minus 0.05. Again, error is huge. So in other words, the arbitrary pole placement does not address at all the issue of steady state errors. And steady state errors may be really, really bad, right? So, but what we can do is we can augment the pole placement with internal model principle to address both steady state errors and transients through pole locations. So how do you do that? Well, we'll present that next. So just a few comments. The complementary sensitivity function would inherit the uncancelled zeros of controller, and hence we might have poor performance due to the zeros of the controller, right? So if controller has an unstable 0, the closed loop, transfer function or complementary sensitivity would have unstable 0 as well. and that would cause undershoots in the step response. As I said, steady state behavior is not easily handled directly by this technique, but you can combine it with interval principle. So how do we do this? So we saw yesterday how to find a generating polynomial gamma, and if we want to track a set of references or reject a set of disturbances, that will give us gamma. So gamma would model all the references you want to track and all the disturbances you want to reject. So this would be typically known from your problem formulation, right? So this gamma would help you achieve zero steady state errors for these classes of reference inputs and disturbance signals. For instance, if you want to track step references, then gamma would be S. So 1 over S means that the controller should contain an integrator. This is what we saw a couple of lectures ago. If we want to track sinusoidal signals, reference signals, of frequency 1, let's say, then gamma would be S squared plus 1. So that would be enforced structure on controller. So how do you use interval principle combined with pole placement? You basically say, all right, I know my plant. My model of the plant is known, right? Now, because I know what class of references and disturbances I want to track or reject, I would know also gamma from a problem formulation. So what you do then, you say, okay, I will combine this 1 over gamma with B over A as my augmented plant. I treat all of this as a plant. I know everything. I know gamma, I know A, I know B. And then the only thing that is left to do is design this PNL. So, but then the story is exactly the same as what we did in pole placement before, because I just changed the plant transfer function a bit, and then I apply the same technique for placing the poles. If you do that, then you would kill 2 birds with 1 stone. You will achieve zero steady state errors, and you will place closed loop poles where you want. So you kill 2 birds with 1 stone. So, what this says is gamma, so generating polynomial gamma, is treated as a part of plant in design, and P and L are calculated from the pole placement technique. All right. So let's consider a particular problem. So this is an unstable plant. Note that there is 1 pole at 1. It's an unstable plant. We want to track sinusoidal references of frequency 2. So the generating polynomial would be S squared plus 4, right? And we want to, we will be able also to reject disturbances at the same frequency, right? With zero steady state error. So what do? Well, we first, write out the augmented plant sort of polynomial A. So I multiply S squared plus 4 with S minus 1. Well, S squared plus 4 comes from the class of references I want to track, and S minus 1 comes from the plant model. The polynomial B is on top, and that's 1. So I obtain here augmented plant model polynomial is this, and B polynomial is this. And I apply pole placement to this, all right? So in this case, the plant order is 3. So I need to pick a controller of second order, right? I need to pick a controller of second order. So hence, L and P polynomials are given here. Now, note this is a tricky thing. So here we are saying let's enforce closed loop characteristic polynomial to be still third order, right? So why am I putting here zeros? Well, it's a tricky thing. Note that I'm saying plant is third order, but that's artificial. The true plant is first order, right? So because because of that, I'm allowed to put here zeros. Why also? I want to design. So by the way, if I do this, I will. You will see that the polynomials in the controller. So the top polynomial with the second order. The bottom polynomial is the first order from the choice that I had. But this will be a problem if that was all there was for the controller, because this thing here is not causal, right? Because I have a second order polynomial divided by zero order polynomial. However, the true controller would also have generating polynomial for references, you know, as part of its transfer function. So actually the full controller transfer function would be, you know, second order. But when computing P and L, right, I enforced L2 and L1 to be zero, right, through this design. So if you do, again, Sylvester matrix, you solve it, again, with the choices that we had, the Sylvester matrix turns out to be lower triangular. Because all the elements on the main diagonal are ones, this matrix is invertible, so we can sort of just solve by multiplying. First we can find the inverse, multiply with this vector, we get this vector. These are exactly the coefficients in the controller transfer function. And this is what you get. So the controller transfer function is P of S over L of S times 1 over gamma. But note here, P is second order, L is zeroth order polynomial, and that would cause problems in general, but not in this case because we still have this gamma polynomial. So the controller is causal and implementable because of gamma polynomial. All right, so what's given here now is, so above you have a Simulink sort of diagram, block diagram. So reference signal is given and it's of frequency 2 because we wanted to track references of frequency 2. And here also you have two different disturbances that are applied at this time and one disturbance is applied at this time, right? So what you have here is that blue line, thick blue line, is basically your reference that you want to track. That's a reference of frequency 2, right, of certain amplitude. And this thin line, look at this really small thin line here, is the true response of the system. So if I don't have any disturbances acting on the system, and I want to just track the reference signal, note that very quickly, thin blue line converges to the thick blue line. In other words, we do get tracking of these sinusoidal references when there are no disturbances. Right? And then what we do here is, at this point here, we hit the system. So by the way, a red line here gives you the shape of disturbance that we are applying to the system. So disturbance is applied there, and at this point, from 0 seconds to 4 point something, or 5 seconds, we have zero disturbance because red line is 0, right? Here we apply high frequency disturbance with higher frequency than 2. So and you can see that the thin blue line goes berserk because, you know, we did not design our controller to reject this high frequency disturbance. We only designed the controller through internal model principle to reject disturbances of frequency 2, but not higher frequencies. So we turned on high frequency signal, but then we set it back to 0. So now again disturbance is 0, and note that again the thin blue line converges to thick blue line very quickly. So again we are back to the scenario that controller was designed for. And then at this point here, about 11 seconds, we hit the system with a sinusoidal disturbance of the same frequency 2, right? The frequency is 2. And note it's sort of shifted off, it's not really synchronized with the reference, but it has the right frequency. And note again that thin blue line first goes nuts, right, for a bit, and then transience is very fast and it converges very quickly to the reference. So what you see here is that the controller is able to track references of the frequency equal to 2 and also rejects disturbances of frequency 2. Note that the error between the thick blue line and thin blue line, in other words, reference output and true output is 0, right, as we go on. But here we do have, whenever we hit the system with some disturbance, there will be some small transient. When we hit it with a disturbance of frequency 2, this will converge to 0, right? The error would converge to 0. Whereas if we just kept this high frequency disturbance, we will never converge to 0. The controller would just not be able to cope with it, right? So this shows you in action how, you know, internal model also principle works, right? On a very sort of interesting example, right? Are there any questions? All right. So this is just a summary. So we get perfect tracking of a reference at 2 radians per second. What would happen if I gave the system reference of 4 radians per second? We won't get 0 steady state error. We won't, right? You can, you know, simulate this example. What happens if I give it a step reference input, step signal? Just look at the controller and plant transfer function. So plant transfer function is this. Do we have an integrator in the plant? No. Do we have an integrator in the controller? No. We wouldn't get perfect tracking, right, of step references, right? Because the internal model principle is not satisfied for that class of signals, yeah? All right, so we also get in this example perfect rejection of disturbances at the same frequency, 2 radians per second, right? So this property is robust in a sense that if you perturb slightly, you know, either the plant or controller, as long as the generating polynomial stays the same and we preserve stability, we are still okay. So even when I change A and B and I change controller or keep the same controller, but the closed loop is still stable, that will still give you perfect tracking because we enforce the generating polynomial on the controller. We control that. We know that it's there, right? So it's robust in that sense. And then we cannot reject high frequency output disturbance or low frequency. So low frequency is step signal, right? So 0 frequency, right? We can't reject that either or track. So if we measure, so this is basically what I cover in advanced control. If we measure input, output, and all the derivatives up to order n, then you can use a static map, static controller that acts on this sort of set of measurements. So, but that's different from what we are doing here. We are just assuming that we measure output. But I'm saying if I measure output, output's derivatives, and input's derivatives, I can use a static map to close the loop and achieve arbitrary pole placement. All right? And that's covered in advanced control. And also I mentioned that this arbitrary pole placement is really related to controller observer design that I do in advanced control. There's a thing called separation principle, and you would end up with something very similar to what we are doing here if you do this design technique. So there's definitely analogy between state space methods and this sort of design that we presented in this lecture. All right, so just to wrap up, we showed several methods for selecting desired pole locations, Butterworth filter, prototype filter, dominant poles. We also saw that for a coprime plant, so in other words, there are no pole zero constellations in the plant, the controller of order n-1 would be able to arbitrarily place closed loop poles, right? So the controller has to be general enough. You have to have enough coefficients in the controller to play with in order to achieve arbitrary pole placement. We also saw that typically you wouldn't use internal model pole placement on its own. You would use it together with the internal model principle because you want to achieve steady state error 0 and also transients to do something, right, that you want. So typically you would combine it, and we presented one example of how to combine internal model principle with pole placement. And then, as I said, coprime condition is related to these properties of controllability and observability. Controllability is basically a property, that says you are able to control your system. So if you have a car, I take out the steering wheel, the car is not controllable. Observability is related to whether I can figure out internal states in the system from measurements. So if I don't measure anything, if I'm a blind person, I can't really see. I'm not. The system is not observable. There's no sensors. The system is not observable. There are no actuators. The system is not controllable. It's much more subtle than this, but these properties are very fundamental to control system design, and they are so lack of controllability or observability is related to pole zero cancellation, right? So, and I make these links more explicit in advanced control. All right, are there any questions? All right, well, tomorrow we don't have a lecture, we have a midterm test. Good luck, and yeah, I will see you next week then. Thank you.
I'd like to ask a question.
Sure.
Can you tell me what the Q and N represent in this case?
So n is just a parameter, so n changes from 0 to q, and q is the highest order in this polynomial. So q in the example we considered was 2, because I wanted to track sinusoidal references. So
it's the highest order of disturbance.
generating polynomial.
Okay.
Generating polynomial. So generating polynomial, you will select depending on which references you want to track and which disturbances you want to reject.
So that's the highest. So say if the disturbance is order of 6, then the generating polynomial has to be 6.
Yeah. So if I, for instance, if I want to track references of frequency 2, and I want to reject disturbances, step disturbances, then I have to multiply s squared plus 1, right, or 2, sorry, s squared plus 4, yeah, s squared plus 4. I have to multiply that with s, because s squared plus 4 is for the sinusoidal disturbances, the references, and s is for step disturbances.
From the reference.
Right, so the total degree of this generating polynomial then is 3, and that depends on which references and disturbances you want to track or reject.
So this is the sum of the highest orders of the reference.
That's right. But if you, for instance, if I tell you I want you to track ramp signals, reference signals, and reject step disturbances, you will still use just s squared, because the s squared can generate both constant signals and ramp signals for different selection of initial conditions. So in some cases, the generating polynomial for reference signals might already contain the generating polynomial for disturbances, and then you don't have to repeat them. Right. So how you select gamma depends on what are the reference signals you want to track, what are the disturbances you want to reject. Right. And then so when you multiply all these polynomials, you will get some order Q.
But then why did the high frequency in that example, you showed that you were tracking the disturbance instead?
I just need to return this, sorry. Because I didn't include high frequency generating polynomial in the design. So let me just so suppose that frequency was 10. Then I'm going to include the generating polynomial.